So in this talk, we are going to talk about anomaly detection in industrial processes. That means that we are going to try to detect when anomalies occur in different engines, different machines. That means that we are going to follow up a machine, a motor, let's say, in this case that will be a motor. That means that we are going to have time series, and in those time series we are going to try to provide tools that enable us to control if there is a problem in the motor or not. Therefore, we are going to use some multivariate time series, and we are going to follow them up and detect what happens when there is a problem that occurs, an anomaly that appears in the system, in the motor itself. Thus, I'm going to give an introduction example before going more to the theory behind that. Thus, I'm going to take examples of motors. We have data coming from the Case Western Reserve University. This university, there is a bearing data center such that you have data from motors. And by themselves in this university, they have, I will say, normal motors and not normal motors. Not normal motors because specifically of the bearing balls, the ball bearings that may have different defaults. And more precisely, they have motors like this. And in those motors, you have ball bearings here and here close to the fan end and here close to the drive end. Thus you have balls here inside, an inner race, an outer race. And they have specific motors such that here they can use a ball bearing for which there is a default, for which there is a problem. There are different kinds of problems, maybe on the balls, in the inner race, in the outer race. And there are different measures around. We can measure at different places on this motor. We are going to have measures such that those measures should enable us to detect that the motor has a problem or that the motor has no problem. Thus, we have motors for which this ball bearing has a problem and motors for which this ball bearing has no problem. But in general, what we want to do is what we want to have is a technique, is a tool that is able to recognize any kind of default. Therefore, in the general case, we want to have a tool that is good, that should be good enough against any type of default. Here, any type of ball bearing default. And we have different kinds of defaults for this ball bearing. Therefore, what we should imagine is that, in fact, we only have motors that are normal. We don't know exactly what are the defaults. Therefore, we should imagine this situation where we only have motors that are normal. And with those data, we should imagine a border, a limit, a threshold, such that when we have specific measures beyond this threshold, in a way, we should detect that the motor is not really normal anymore. Therefore, we should imagine that we have a set of normal motors. We are going to provide a tool that enables to say if this motor is not normal, that if this motor has a problem or not. And in the second step, obviously, we will use the motors that we know that they are not normal, and we will see if the procedure detects that the motors are not normal. But I think you understand the objective. The aim of this talk is to say, okay, we don't know what could be the default in theory. We only have motors at the beginning. We only have motors that are fully healthy, I would say, that are normal. And we want a procedure that, okay, maybe there is a model that appears anywhere. Thus, it's possible that the model doesn't work anymore. We want to have a technique that detects if a model doesn't work well anymore, but we don't know which kind of default. Therefore, we need to find a procedure which is able to detect anomalies for any kind of defaults. Therefore, that means that we should only construct a methodology that creates a border in a way that defines what is a normal model. We have this. Specifically, there are different measures. There is a torque which is measured. There is a force with the dynamometer. There is a control electronic. But there is more important vibration signals that are collected using accelerometers. An accelerometer close to the drive end, another accelerometer close to the fan end, this close to the bearing, the first one close to the drive end. That could be an accelerometer that measures the ball bearing with a possible default. And here close to the fan end, maybe we have vibrations measured close to the fan, and in this case the ball bearing close to the fan hand has no default. The machine that we will insert in a second phase when the tool is constructed, the machine that we will insert in the system, the motors that we will insert, will maybe have a default, but this default will be close to the drive end. Thus, okay, now we can go further, saying that there is a specific data set that we took with a lot of data for the training phase. That means to construct the tool, and a lot of data as well with 500 samples to see if the tool that we construct correctly detects abnormal motors. Here we will use 500 samples, and we will have to detect that those motors are well detected as motors with defaults. And thus we have specific motors that have no motor load. That means that there is no load on those motors. Therefore, they run, and when measuring the vibrations of them, we should detect those motors have no load, and we should detect if they are abnormal or not. Thus, the detection of anomalies should be made in 2 steps. The first step consists of constructing a model for normal time series of vibrations. We're going to construct a model for those normal models that will be made with a long short-term memory autoencoder. We're going to explain that just after. And if we have a normal model, that means in a way that we explain something with something else for the normal models. There is a law inside the normal models. We construct a law related to the normal models. Then that means that if we use a given motor, if we insert a new motor in this model, we should have, in a way, errors of this model which are small if the motor works correctly, and those errors of the model should be larger if the motor goes wrongly, if the motor has a problem. Thus, that means that with this model, we construct a model. We have residuals for this model. This model is very good for motors that are working well. This model is very bad should be very bad for models that are not working well. That means that the resulting errors of this model should be larger for models that do not work well with respect to models that work well. Thus, the second step will be, okay, we are going to try to find a threshold, to find a border, such that beyond the border we detect, we assess that the model doesn't work correctly, and inside this border we have a model that works correctly, and we will use for that a one-class support vector machine. There's two steps, and the first step is how is it possible to construct a model on multivariate time series of vibrations in this case. This most of the time, to construct a model on data like this, in data science, in machine learning, we can use neural networks adapted to time series. That is named, in this case, recurrent neural network. Thus, for a classical recurrent neural network, we assume that we have data x1, xp, p dimensions, p variables, measured at times, at different time steps, t equals 1, 2, 3, 4, and so on. And we have an output, the output ht, denoted ht with m dimensions. That can be prediction of the next m values, that can be anything else. That can be prediction at the time t plus 1, that can be a lot of things. This is an output. This is a target. This should estimate a target, and this is the output of the network. Sometimes there is still a small operation on this HT to get the real output, but basically this is what I want to say here, the input here and the output of the neural network, which should be close to the target. And a neural network, recurrent neural network, is very close to a classical multi-layer perceptron, for example. That means that we define nets. Nets, this is the shape of a cell, a unit, a neuron, and here you have a lot of synapses and inputs for those synapses. That is a net. That is simply a net, and we defined here in this case the net T for the cell I. In the case of recurrent neural network, when we have dependence on T, and this is, as in a classical multi-layer perceptron, I would say, a sum of weights that goes from J to cell I, J equals 1 up to P for P variate, times xt of J, that's different components of the vector X. That means the input. This is classically what we have in a neural network, the net of a neural network, but here we also have an enrichment from the past. And what is the past? This is the output at time t minus 1, the output of the neural network just at the previous step. Therefore, we have a sum from j equals p plus 1 up to m plus p, m this dimension, of weights from a cell to another cell, to the cell I, of ht minus 1, but evaluated at g minus p to have a cell here for this h, which is between obviously 1 and m for the output. Thus, here we have the general formula for a net in the case of recurrent neural networks, and this net is transformed at the end of this step through an activation function fi. This is here, for example, a hyperbolic tangent to get the output here. And we can see here what happens at times xt. Times xt is combined with the past ht minus 1, such that together, both together, they consist of the net, and the net is transformed through here a tangent hyperbolic function, such that we have ht here. That is the block, that is the main block, I would say, of a recurrent neural network. But there are problems with this kinds of network, especially when we use a gradient descent to update the parameters w, I, j of those networks, w, I, j here. The gradient contains derivatives of the loss function. Derivatives of the loss function, and the loss functions contains terms of this type. dti, this is the target of the cell I at time t. Therefore, that can be a prediction, for example. And hti, this is the value which is predicted by the recurrent neural network at time t for cell I. And thus we have terms of this type. The derivatives of this square with respect to wij. And when you compute this derivative, in fact, it involves terms. It's easy to write this derivative as a function of the partial derivatives with respect to net tau for the cell I, for a tau which is smaller than t. Therefore, this derivative can be rewritten as a sum of terms, and in those terms you have factors of this type. But when you write this kind of things, is governed, is in the theory of neural networks, by backpropagation algorithms most of the time. We talk about backpropagation algorithms. That means that those values are computed thanks to the values, the same values of this, but at time tau plus 1. And you go, you backpropagate the error flow. We name that like this. From the fact that you know this at time tau, it's possible to immediately compute it at the time tau minus 1, and after at time tau minus 2, and so on. You backpropagate the error flow. This is what we say in the language of machine learning in this case, in the case of neural networks. But the problem in this backpropagation formula, which is roughly a chain rule, this is a chain rule in mathematics, is that when you do this operation, that results in products of derivatives of activating functions that can be in practice very small or very large. You have an activation function, and the slope of this activation function can be very close to 0, can be very very large, if for a sloppy for a curve with a very large slope in the activation function. And this, due to precision of the machine as well, it's possible to have values that are very small and even 0 in a way, and those slopes in those derivatives. And we have a product of things like this. And the number of factors in such products, due to backpropagation, the number of factors exactly equals t minus 2 in each sums that are involved. That means that if you multiply things that are smaller than 1, if you multiply them too much, you really, it's possible that you very quickly reach the 0. If you have something that is 0, that means that at the moment your different derivatives here are 0 as well. That is what is named the vanishing gradient problem. If we have derivatives that are very high, in this case you have the problem of exploding gradients. But what happens often is that you have the vanishing gradient problem. That means that if t minus tau is too large, you have full parts of the gradients that vanish, that goes to 0, and that means that in this case you have weights that are updated thanks to those parts, but updated only with recent contributions. That means contributions like this for the update of the W in the gradient descent, but with tau which is very close to t. If tau is too far from t in the past, in this case the contribution is 0 or close to 0. That is the problem. This is the vanishing gradient, and to solve this problem we are going to use a more complex memory block, a more complex neural network that involves gates, input gates, output gates mainly, to make the error flow in a way such that they don't go to 0 too quickly. And in fact the idea for this is similar in a way to the recurrent neural network, but it's more complex here. But basically, I explained that in 2 or 3 words. We also define a net, but now we have different cells. We can have cells that come from what we will name an input gate, an output gate, a forget gate, or the cell gate. The cell which is the treatment, the general treatment that will give the output. And this, for each of those 4, I would say, neural networks, we have nets. M can belong to those 4 possible neural networks. And Mj here, that denotes a cell inside one of those networks at time t here, and we add the 1 here to say that this is the layer 1. After we will see the formula for layer L. And this is very close to what we have seen for recurrent neural network. We also have a combination here of the new variable that are entering the system, xt, combination of them, plus the past. And the past, what does it consist of? This is the output of the neural network at the previous step for the cell state, for the cell, for the main line, the main part of the neural network, but at the previous step for cell Cj, and we have an output, the output, but not necessarily the output. This is the output if you only have 1 layer. But in fact, this is the output of the first layer, not the output of the whole neural network, but the output of the first layer. Therefore, in fact, this is very close to what we have seen for a net in the case of recurrent neural network. What the new data that enters and the output of the data at the previous time, the output of the first layer. And if we go further in the layers, at the layer L in this network, we will have the transformation of xt at layer L-1, transformation through the activation function through the cell Cj. Thus this is xt transformed up to the layer L-1. And what comes from the past, but at the layer L. That means the data transformed up to the layer L, which is already calculated in a way, in a forward pass like this. Thus you have the activation function at the layer L, but for the data at time t-1, the transformation of the data at t-1, but up to the layer L to enrich the information in this net. And obviously this net is transformed. This net is transformed thanks to here sigma ml, which is an activation function as well, that transform the net at time t and at the layer L. And we can see it on the graph here what happens. We can see on the graph what happens. And we are going to describe it. When we have those formulas, we can write the pre-output, I would say, of the cell this the data that will be the output of the final network. Not exactly the output, but just before the output, we are going to make combinations like this. We first go from 0 at time 0, but progressively we write this this combination. In this combination, what do you have? You have this main, I would say, NetTL, like a recurrent neural network, that you transform through an activation function, HL star, and at the layer L, HL star, this is an activation function. This is not complicated. This is another activation function. And it's multiplied here by a recurrent neural network, I would say, but for the input gate. Therefore, we take the cell, we take the cell at the time t, and we multiply it by the input gate, and we add the information from t minus 1, the cell at t minus 1, and we multiply it by the forget gate. The input gate and the forget gate are two gates that are of the form of a recurrent neural network. But we multiply recurrent neural networks in a way in order to stabilize the error flow in a way. That's the idea with respect to the vanishing gradient problem. You can see it like this here. Here we have xt, we have data that come from the past that are ht minus 1, ht minus 1, t minus 1, it is the information that comes here. You have information at SSLT minus 1 here, times the information at time, times the information at time t. Those two things are involved here, and there is here an activation function. This we take what we name the forget gate, we multiply it by the information at time t minus 1. This is the forget gate. And the forget gate here is we have a multiplication. We have the information at time t minus 1 that goes information at time t minus 1. It's here. Information at time t minus 1 and xt together. Here they consist of this transformation. Here you have HLT of phi j. This is the forget gate with this sigma, which is an activation function. It's multiplied by information at time t minus 1 here. St minus 1 L of Cj comes here. This is this factor, this term, sorry, and then we add also this information coming from the past plus information coming at time t, and here multiplied, transformed by an activation function, and that is here the input gate, which is here. Also the same thing, but with the cell itself. This is multiplied here by HL star. We will say here we represented it by the we consider the hyperbolic tangent for it, and we have this product here. And then those two things are added here. Those two things are added. They go that way, and finally here this quantity. Therefore, HL star star here of this quantity, that means an activation function as well for this quantity, which is here. This is also a hyperbolic tangent. Is multiplied by, again, a network of this type, which is the output gate, and therefore this multiplication is here, and H arrives finally here. And H at the time t here can be transmitted to the next memory block at time t plus 1. Here you have HT that goes, here you have ST, that goes from this block to this block, and that can be used for the next block in the same way as we did up to here. This is the idea of LSTM, long short-term memory networks, and that's the idea that is used to remove the vanishing gradient problem. Next, we want to construct a model. We want to construct a model. That means that we want to describe what happens. We want to describe what happens in the machine. We don't necessarily want to predict the next values of vibrations. We want to correctly describe a normal machine, a normal motor, with the main features corresponding to the main features of the vibrations. That means that we are going to construct, in fact, LSTM, what is named LSTM Autoencoders. We are going to construct a model that describes the vibration as a function of the main features. This is the idea. And we are going to construct this model for normal motors. If this model is applied to a non-normal motor, it will provide big errors. How do we construct that? We divide the problem into two LSTM problems. The first one is the encoder, and the second one is the decoder. That means that we are going to take the multivariate time series. We are going in a way to encode them here in a specific space, the space of encoded data, the latent space, we name it, of smaller dimension. Therefore this hidden space will contain the main features of normal motors. And then, thanks to a decoder, we are going to retransform, to take those encoded data and retransform them to decode them. And here we have the decoded data. And X hat will be the decoded data. X will be the data that are the input of the model. And then we will use this loss function. This loss function will obviously be the difference between the decoded data and the input up to the square, and the norm 2 of that. That means that we have, in this case, a norm 2. We will have X hat minus X with a norm, an Euclidean norm, sum of squares, of squares of all the components for X hat minus X. Therefore, we will have XX minus X. This will be X minus the decoded data, and the decoded data, in fact, this is the decoded, the data, the encoded data that are decoded. Therefore, X can be represented by D of E of X, the encoded X, which is decoded after in the second step. This is what we're going to do. There's two LSTM autoencoder. Two LSTM networks. The first one transform this into this, and the second one transform this into this. To improve the performance of this, when we have transformed x1 xt, we are going to revert it. We are going to reconstruct it, but in the reverse order. We're going to begin from xt, x capital T, if we have a time series of length t that we enter in the encoder, and we are going to reconstruct xt first, xt hat in the forward pass, and after x hat t minus 1, x hat t minus 2, up to x hat 1. And this is done with a classical neural network. Here I'm going to I just give the formula as well to reconstruct in the opposite sense, in reconstructing the a time series, a multivariate time series, in the reverse order. That means that, in fact, let's take at time t minus 2, for example, For the t minus 1 case, this is the same formula, but you should remove this term. It's not complicated. But at t minus 2, let's say, then the net at t minus 2 will be this quantity. If L equals 1, for example, that corresponds to the encoded data. The encoded data they enters, the encoded data that are here, they enter, and this the net, let's say at the first layer at t minus 2, this is the encoded data, but we're going to take it at the time t exactly, not t minus 1, because there is more information, in fact, for the encoded data at time t. Therefore, for every construction of net here, we will use the encoded data as the encoded data at time t. This here, the net, is a combination of the information of the encoded data at time t and the previous, I would say, previous decoded data. Previous decoded data, that means something, that means data which has been transmitted. If there is only one layer, this is data that has been transmitted to the decoder. Therefore, this is an activating function at layer L, one layer later. If L equals 1, this is a decoded data, but at the previous time. But since we reconstruct the series in the reverse order, the previous time, this is in fact t minus 1. If we want something at t minus 2, we need the decoded data at t minus 1, which is the previous one in the way we reconstruct the data. And this here we have possibly L layers, therefore we can extend it by saying, okay, the net at layer L, this is the net for the encoded but already decoded data up to L minus 1, a combination of this, and here not exactly the decoded data at time t minus t plus 1, but the pre-decoded data, that means the data that has passed through layers up to layer L. Because we reconstruct the series like this, we take the output decoded data minus input data, and we have the errors. We have the errors, and now we are going to separate the errors in the second phase. First phase, we have a model and we compute errors. Second phase, we are going to use a one-class classification algorithm to separate large errors, two important errors, from small errors for normal engines, normal vibrations. And we separate, in fact, the idea is to use the one-class support virtual machines, which separates the origin 0 from the other data points with a maximal margin, as small as possible. We're going to do something like this. We're going to find a margin here. This is a hyperplane. This is a hyperplane in a space of large dimension, which separate as most as possible the origin from the points. And in fact, that means that we are going to use a hyperplane with this equation, WT times the errors equals rho. That will be the equation of this hyperplane, and we can show that in this case the distance between the origin and the hyperplane is rho divided by the norm of W. W, this of dimension p, epsilon t of dimension p as well. Now we consider that we have for the whole data set n data points. We use this Euclidean norm here to have this. It's possible to calculate that very easily, and thus the idea is to maximize this quantity. And that amounts to minimize this quantity. You see this function increases with rho, decreases with W. This function increases with W and increases with W and decreases with rho. Therefore, if we minimize this, that should amount to maximize this. And we minimize this with respect to W and rho. That is the objective function. But obviously, we don't want to have all the points beyond the hyperplane. We want that the hyperplane separates normal point from not normal points. That means that we would like to have this hyperplane further here, such that those points only are outliers and could be defined, could be said to be abnormal data. We are going to introduce slack variables, and we are going to transform the constraint W epsilon larger than rho into W epsilon larger than rho minus rho t, where rho t is a slack variable. We are going to make it as small as possible, this rho t, by putting it in the objective function as well with this new parameter here. Therefore, those quantities are larger than 0, and we have this new objective function. Now, with that, you derive that with respect to rho, with respect to W, with respect to C, the solution, you reinsert it in the objective function, and you take the dual Lagrangian problem corresponding to that. It's possible to show that in this case, the dual Lagrangian problem corresponds to this, where the alpha here are the Lagrangian multipliers of those constraints. You also have gamma multipliers that corresponds to those constraints. Thus, the idea is to say, now I'm going to solve the dual problem, the dual Lagrangian problem, and it consists of minimizing with respect to alpha this quantity. This scalar product here can be replaced by a kernel, by the Mercer theorem. You have a product, this is a sum of things, this sum of things, you can transform it in a sum in a high dimension space, and this sum in high dimension space can become a kernel, classically a Gaussian kernel as it's defined by the Mercer theorem. And thus at the end, we have the values of this alpha, and that means that we can compute from this the values of W, the value of rho, and it's really important to classify data. As soon as we have solved this problem, this minimization problem, we are able to classify a new point with the solution that we have for W and the solution that we have for rho. We can see on which side of the hyperplane the point is. Obviously, this new parameter is very important. This new parameter can be rewritten as 1 over n times q. And it's possible to see that q in this case is a lower bound of on the number of the fraction of supervectors. Supervectors are defined as the points for which you have a Lagrange multiplier which is not 0. That means a Lagrange multiplier which is not 0, that corresponds to a constraint which is saturated, which should be where we should have an equality here, an equality that corresponds to a support vector. Therefore, an alpha which is different from 0 corresponds to, this is the definition of a support vector in the one-class support vector machine. Just with all that, we are able to play with this value nu, which could be equals to 1 over n times q. As I said, this q is a value. We can play with this value in a way to have an idea of what is lower bound on the number of support vectors, and therefore in a way what is the fraction of outliers that you have in your database. And here we have some results with some things that are chosen, some parameters that are chosen by cross-validation, some quantities that are chosen here. And we can see that we have, I'm going to skip this and immediately go to the results here, this kind of results for which you see that all the red points are outside the border. That is a good signal, and all green points are inside the border. Here the machine is assessed, the vibration is assessed to be normal. Here it's assessed to be non-normal. Therefore, we have to compute for this precision recall F1 score and accuracy. Therefore, the probability of a red point to be detected when it's red. this is 99%. The precision, the probability, if you are outside the blue border, the probability that you are a red point if you are outside this border, this is also a good quantity here. And the harmonic mean of those two quantities, which is relatively high, this is the F1 score, and the accuracy, which is the proportion of classification errors here, which is relatively good as well. We have made a comparison with a basic quantile estimator. If you want, we can also take a basic quantile estimator of the squared errors, the Euclidean norm of the errors of the epsilon hat. We could construct a quantile estimator and say, okay, for a given quantile, I'm going to choose the one that gives me the smallest error. Therefore, it's not a technique that can be applied, but that could be applied in practice, because you have to choose the quantile. And here, if we choose the best quantile for this quantile estimator, that means a quantile that separates the norm 2 errors of the vibrations. If we choose the best quantile, we have a lot of possibilities. We reach those digits, and those digits are less good, in fact, almost as good as those digits here, but less good than this digit, and you have to choose this parameter. Here, for the parameters that we choose, if we play a bit with the parameter, the results here do not change a lot. Obviously, there are still a lot of works that can be done with that kind of methodology for anomaly detection, but for now I'm going to stop, because I think time is I think that I've said the most important things, and therefore we can have more discussions about that.